So now let us look at the RX design or IEEE 802.11g standard. The first specification we are going to look at is the sensitivity. So as per the standard, the sensitivity is given as minus 65 dBm for 54 Mbps data rate, which uses 64 QAM modulation with the OFDM. High data rate requires more complex modulation. For our design also, we will assume the specifications which are given for 54 Mbps data rate. And for this case study, we are going to ignore the other data rate specifications. And for this 54 Mbps, the minimum SNR given is 18.3 dB. So as to meet the error rate requirement. So we can find the noise figure of the receiver based on the specs given for 54 Mbps. So we know the sensitivity is equal to minus 174 plus 10 log B plus the noise figure plus SNR min. So SNR min we already know, the sensitivity we already know from the standard. This bandwidth, the channel bandwidth is 20 megahertz, but the occupied bandwidth is 16.6 megahertz. So this is what we are going to use for our calculation. And based on this, we can find out the noise figure. So if we plug in the values, we are going to find the noise figure to be equal to 18.5 dB to meet this spec. And in all the real systems, you will find that there is going to be attenuation at the antenna interface. In addition to that, you will also add some design margin. And we can say that the target noise figure for the entire receiver is going to be 10 dB, assuming 8.5 dB margin. So the next specification for the receiver is its linearity. So this RX linearity can be found out from the standard. So the standard gives two aspects of the receiver. One aspect talk about the maximum input signal power which it needs to handle. Indirectly it tells us what should be the compression point of the receiver so that the receiver doesn't saturate. And second specification we get from the standard is about strength of signal which is going to be present in the adjacent and the alternate channel. Due to adjacent and alternate channel. So we can very quickly see this scenario where we have signal present in the adjacent as well as alternate channel. So let's say this is our desired channel. This is the F channel. Now standard says that we need to handle signal in the adjacent channel, which is going to be 16 dB higher than the channel power. And this specification we have to meet when the channel power is just 3 dB above the sensitivity value. So this P channel is equal to minus 62 dBm, whereas this P adjacent channel is equal to minus 62 plus 16, which is equal to minus 46 dBm. And in addition to this adjacent channel, you also have to handle power in the alternate channel, which is going to be minus 62 plus 32 dB higher as per the standard, which is going to give us minus 30 dBm. So when we are trying to receive signal in our desired channel, these two signals can also be present at a much higher strength, and their intermodulation can give rise to the intermod component in the desired channel. So we can get an IM3 because of these two signals. So these in-band blockers have to be handled by the front end, and only before the digitization it is going to be filtered by the channel select filter. So now we need to look at what should be the IIP3 of the receiver so as to make sure this IM3 component, because of this intermodulation, is much below the noise floor in the channel. So let us look at both of these aspects and find what should be the linearity for the receiver. So let's take the case for the maximum input signal power. So the spec says we need to handle minus 30 dBm maximum average power at the input. And for the data rate which we are looking at, you'll find that the peak to average power ratio of the input signal is going to be around 9 dB. So the PAPR is 9 dB for 52 Mbps data rate case. So it means we need to make sure the receiver can handle 9 dB above the maximum input signal power so as to not cause any kind of clipping. So we need to ensure that P1 dB to be minus 30 plus 9 plus some extra 2 dB margin we can add to account for any envelope variation due to the pulse shaping. So it means we need to make sure the P1 dB of the receiver is going to be equal to minus 19 dBm, which implies the IIP3 should be equal to minus 9 dBm. Now this is for this Pmax case. Now if we look at the in-band blocker due to signal in the adjacent and the alternate channel, let's call the amplitude in the in-band to be A0, in the adjacent channel to be A1, and alternate channel to be A2. Then their IM3 can say that the IM3 should be at least below the noise floor by some margin. So the SNR we are trying to maintain in this case is around 18.3 dB. In addition to that, we can add some margin. So in the presence of other non-idealities also, the noise floor is not disturbed. So we can say that it should be at least 18.3 dB below the channel power with some margin. Here we are taking 10 dB margin. So this will be equal to minus 28.3 dB. And we can find this IM3 ratio as 3/4 alpha 3, which is the coefficient of the third order term in the output-input relationship, into A1 square, because here we are looking at the 2F1 minus F2. Let's call this as FC, F1, F2. So the intermod is going to appear at 2F1 minus F2, which will be equal to FC in our case, into A2 divided by the fundamental strength, which is alpha 1 A0. The 20 log of this entire ratio is your IM3 ratio, should be equal to minus 28.3 dB. So if you take the values of A0, A1, A2 based on the power levels given by the standard, then we can find that the IIP3 turns out to be equal to minus 16 dBm. So the IIP3, because of the maximum input signal power spec, is coming out to be minus 9 dBm, whereas because of this in-band blocker, we are getting minus 16 dBm IIP3. Now, one point to note here is that when we talk about the maximum signal power, we may reduce the gain in the receiver. So under those reduced gain, we need to meet this minus 9 dBm specification. Whereas for this in-band blocker case, we are talking about the signal which is close to the sensitivity level, only 3 dB above the sensitivity level. So in such a scenario, the receiver is going to have a very high gain. And under that high gain condition, we need to meet this minus 16 dBm IIP3. Need to meet at high gain mode. Okay, finally, let us talk about the range of the gain which is required for the receiver. So if we are assuming that the receiver is driving an ADC which has a full scale, let's say around 0 dBm, ADC scale, let's say 0 dBm, then we need to make sure whatever may be the input power, after passing it through the receiver, we are close to the full scale of the ADC. And if the full scale is 0 dBm, then in the presence of PAPR as well, we need to make sure there is no clipping. So it means the output power of the receiver key out should be 0 dBm minus PAPR, which in our case is 9 dB, plus there can be variation in the envelope. So let's keep a 2 dB margin there. So this is going to give us output power at the RX2B minus 11 dBm. And the input power, we already know that it varies from minus 65 dBm, which is the sensitivity, till minus 30 dBm. this implies the gain range is going to be the G max will be minus 11 plus 65, which is 54 dB, and the minimum gain when the input signal is at its maximum value, minus 11 plus 30, which is equal to 19 dB. So now we know the noise figure, linearity, and the gain spec for the receiver. And based on this, we can try to design the receiver front end, which includes the alignment mixer. And in this receiver, we can put all the gain tunability in the analog baseband circuitry. One point to note here is that we need to maintain this noise figure of 10 dB for this maximum gain case. And as the input signal starts increasing, we need to reduce the gain, and at the same time we can also allow the noise figure to degrade because the received SNR is also increasing.